Hi friends, in this video we'll discuss about the bivariate distributions and their properties, distribution of sums and quotients and conditional densities. So we'll say this is also giant probability distribution. What is a giant probability distribution? In general, if capital X, comma capital Y, so on, capital P are n random variables, the probability distribution that defines their simultaneous behavior is called a giant probability distribution. When there are only two random variables of interest, we all use the term bivariate probability distribution or bivariate distribution to refer to the giant distribution. There are two types of the giant probability distributions. Giant probability mass function of the discrete random variable of x and y is p of x comma y, and giant probability density function of the continuous random variables x and y is f of x comma. So examples for the discrete random variables is a price versus a demand taken, year in college versus number of credits taken. So for the example for the continuous dosage of drug versus blood compound measures. So these are the examples for the giant probability discrete random variables and the continuous random variables. So we'll see what is the bivariate distribution. For both the discrete and continuous random variables, we will discuss the following. One is giant distributions for two or more random variables. Second one, marginal distributions computed from joint distribution, conditional distributions, and giant cumulative distribution function independent of for random variables capital X and capital Y. So this is the capital X and capital Y are two random variables and their corresponding elements x1, x2, x3, so on, xn. There are m elements for the random variable capital X. Similarly, for random variable capital Y, the elements are y1, y2, y3, so on, yn. So their giant probability P of this x1 comma y1 we denote with P of x1 comma y1 is the probability, giant probability of the elements x1 comma y1. This is giant probability of the elements x1 comma y2, giant probability of P of x1 comma y3, so on P of x1 comma yn. Similarly, probability of x2 comma y1 is the probability of elements x2 and y1. This is probability of x2 comma y2, so on probability of x2 comma yn. For xm, this probability is probability of xm comma y1, probability of xm comma y2, so on probability of xm comma yn. Now, if I'll add all these things, so that means probability of p of x1 comma y1, p of x2 comma y1, p of plus p of x3 comma y1, so on. This one is called marginal probability of y1. This is so, and we denoted by p capital Y of y is equal to probability of y, so is equal to summation x probability of x comma y. So this is x equal to 1 2 3 4. If I add all these things, that is probability of x1 comma y1 plus probability of x2 comma y1, probability of x3 comma y1, so on probability of xm comma y1 is called probability of y1. So this is called marginal probability of y1. Similarly, if I add this complete first row, what happened? Probability of x1 comma y1 plus probability of x1 comma y2 plus probability of x1 comma y3, so on. Probability of x1 comma y1 is nothing but summation y probability of x1 comma y. Sum of all these probabilities called marginal probability of x1. So to get the marginal probability of x is equal to probability of capital X equal to x, marginal probability of y equals to probability of capital Y equal to small y. So if I add all these probabilities, it is called probability of y1. So marginal probability of y1. Sum of all these probabilities are called marginal probability of y2. So on. This sum of all probability p of x1 comma yn, x2 probability of x2 comma yn, so on probability of xm comma yn is called probability of yn, which is marginal probability of yn. These are called individual probabilities. Sum of all these probabilities are called marginal probability of x1. This is sum of all these are called marginal probability of x2, like that xm probability of xm comma y1, probability of xm comma y2, so on probability of xm comma yn is called marginal probability of xm. So that The marginal probabilities of y are marginal probabilities of sum of all marginal probabilities of x or sum of all marginal probabilities of y equals to always 1. So joint probability mass function. The joint probability mass function of the discrete random variable capital X and capital Y denoted by P of capital X comma Y of X comma Y, which is nothing but probability of capital X equal to X, capital Y equals to Y, and it satisfies the condition probability of capital X comma Y of X comma Y greater than or equal to 0 and summation double summation of P of X comma X of X comma Y is equals to 1, then the function P of X comma Y of X comma Y is said to be joint probability mass function. Similarly, as we discussed earlier, marginal probability distribution. If we are given joint probability distributions of capital X and capital Y, we obtain the individual probability distributions of X or Y, which are also called marginal probability distributions. If capital X and capital Y are discrete random variables with probability mass functions, then the marginal probability mass function of capital X comma Y denoted by P of X, which is nothing but the probability of capital X equal to X, is nothing but summation of Y probability of X comma Y. And P of capital Y of Y equal to a probability of Y of Y is called marginal probability distributions. Now, cumulative distribution, it is represented by capital F of X comma Y and defined by capital F of X comma Y equal to probability of capital X less than or equal to small x and capital Y less than or equal to small y is nothing but summation of X, summation of for Y, P of X comma Y. Test of independence. Two random variables are said to be independent if and only if the joint probabilities is equal to product of their marginal probabilities. That means probability of X comma Y equals to probability of X into probability of Y for all capital X and capital Y. Then the two random variables are said to be independent random variables. Now let's go for the one example. Let capital X and capital Y are two numbers sided up. When a pair of dice is thrown, the joint probability can be shown like this. So capital X is indicating number of outcomes on first die, capital Y is indicating outcomes on second die. If I'm rolling off two dice, first 1 comma 1, so that is called probability 1 comma 1 is on first die 1 occur and second die 1 occur. So possibility is 1 out of 36. Now what is P of 1 comma 2 means? First die 1, second die 2. So 1 comma 36. P of 1 comma 1 by 36. So on. P of 1 comma 6 equal 1 by 36. Similarly, P of 2 comma 1 1 by 36. 2 comma 2 1 by 36 like that. P of 2 comma 6 equal 1 by 36. So if I this one P of 6 comma 6 is also 1 by 36. If I add all these things, that means P of 1 comma 1, P of 2 comma 1, P of 3 comma 1, P of 4 comma 1. Like this is called marginal probability of y equals to 1, which is 1 by 6. This is marginal probability of y equals to 2. This is marginal probability of y equals to 3. This is marginal probability of y equal to 4, 5, 6. So if I add all these things, then that is probability of 1 comma 1 plus probability of 1 comma 2, probability of 1 comma 3, so on probability of 1 comma 6 is a marginal probability of x equals to 1, which is 1 by 6. This is marginal probability of x equals to 2, like that is marginal probability of x equal to 6. Again, sum of all marginal probabilities of x is 1, sum of all marginal probabilities of y is also 1, right? So this is the table, the example for the joint random distribution. Consider two random variables A with a x belongs to 0, 1, 2 and y belongs to 1, 2, 4. The following table gives the giant probability mass function. So x values are 0, 1, 2, y values are 1, 2, 4. So 0 0.1, 0 0.1, 0 and 1, 0, 1 comma 1 is 0 0.2, 0 0.1, 0 0.1, 2, 0 0.2, 0.2. Now we have to compute what is the mean, expected value of x, expected value of y, conditional density function of x for given y, and f of 1 comma 4, and test whether capital X and capital Y are independent or not. So this is the table is given, x values are 0, 1, 2 and y values are 1, 2, 4. So probabilities are 0.1, 0.2, 0.3. If I add all these things, then this is marginal probability of y equals to 1 is 0.3. If I add this column, this is marginal probability of y equals to 2. If I add this column, marginal probability of y equals to 4. So if I add all marginal probabilities of y, 0.3 plus 0.4 plus 0.3 equal to 1. Similarly, if I add row wise, 0.1, 0.1, this is marginal probability of x equal to 0. This is marginal probability of x equal to 1, marginal probability of x equal to 2. If I add all marginal probabilities of x is 1, as well as marginal probability of y is also 1 itself. Then marginal probability distribution of x is this one. So x equal to 0, 0.2, x equal to 1 is 0.4, 0.4. Marginal probability of y is 0.3, 0.4, 0.3. So this is p of x equal to 0.2. P of marginal probability of x equal to 1 is 0.4. Marginal probability of x equal to 0.4. Similarly, this marginal distribution of y is 0.3, 0.4, 0.3. So what is the expected value of x equal to? X into probability of x. So 0 into 0.2 plus 1 into 0.4 plus 2 into 0.4, which is equals to 1.2. What is the expected value of y? Summation y into p of y equal to 1 into 0.3 plus 2 into 0.4 plus 4 into 0.3, which is equals to be 2.3. Now, what is the formula to find the conditional conditional density of capital X for given y is we denoted by p of x by y, and we defined by p of capital X by y equals to probability of x intersection y by p of y. So p of x of 0 by y equal to 1 equal to p of 0 comma 1 by marginal probability of 1. So 0.1 by 0.3, which is 0.3. Now, what is the probability of x equal to 2 for given y equal to 4 is probability of 2 comma 4 by marginal probability of 4. So 0.2 by 0.4, 0.667. Now, what is the capital F of 1.4 is? So probability of x less than or equal to 1 and y less than or equal to 4. So x equal to 0 to 1, y equal to 1 to 4. So p of x comma y equal to x less than or equal to 1. So 0.1, 0.1 plus so on. So this is 0.2, which is nothing but 0.6 is the value. So test for the independence. So two random variables x and y are said to be independent if p of x comma y equal to p of x into p of y. So p of x of 0 into p of y of 1 equal to 0.2 into 0.3, 0.06, which is not equal to p of 0 comma 1. So x and y are not independent random variables. Suppose, one more problem we'll move to. Suppose two batteries are randomly chosen without replacement from the following group of 12 batteries: 3 new, 4 used, and 5 defective. So let capital X denotes the number of new batteries chosen. Let capital Y denote the number of used batteries chosen. Compute joint probability distribution of capital X and capital Y. Mean number of used batteries chosen. Test whether the selection of new batteries is influencing the selection of used batteries or not. So the total number of batteries are 12. Given that X, I am assigning number of new batteries chosen, and Y, number of used batteries are chosen. Then the giant probability distribution can be given as X is the new batteries, so 0, 1, 2. Y values are used batteries 0, 1, 2. So 0, X is used to versus this is new versus this, then this is 5C2 by 12C2, right? So this is 4C1 into 5C1 by 12C2. This is 4C2 into 12C2. Next, so 1, then this is 3C1 into 5C1 by 12C2. So 4C1 into 3C1 by 12C2, 0.182 and 0. So this is marginal probability of x equals to 0. This is marginal probability of x equal to 1. Similarly, 2 comma 0. So then 3C2 because 3 new 3C2 by 12C2. This is 0, 0. So this is marginal probabilities of x are 0.272, 0.409, 0.046. Similarly, marginal probabilities of y values are 0.424, 0.485, 0.019. So sum of all marginal probabilities equals to 1. Next, so marginal probabilities of x and marginal probabilities of y are given respectively. The mean number of the